First, we will go for the renewable source of energy. It becomes easier for us to understand also. Now, renewable energy resource like, or a renewable energy source like. Now, what are the examples that we normally highlight for this renewable resources?
Solar, wind.
Good. So we can have solar as one, we can have wind as another, we can have tidal energy also, we can have ocean thermal energy conversion, all those things and all, wave energy, all these aspects like, all these aspects like. Biofuels, there was another participant who told that it is not belonging to this one, renewable energy. We will see how basically, or what basically it is like. Okay. Now, how do we define renewable energy source? When do you call an energy source as a renewable energy resource?
After using, can be used again also.
Sir, please, sir. After
processing, we can use the same solar energy again.
We can use the same solar energy again and again. I don't think so, sir, because once when we harvest them, the energy that is available in the solar will lose, like, right? Likewise, wind, once when we are able to harness it, the velocity will become lower. What is the broad way in which people define renewable energy source, or what is a renewable energy source?
It's a naturally available source.
Coal is also available naturally. Oil is also available naturally. When do you call a source as a renewable energy resource?
Sir, in a particular time, it's renew. I mean, just अपने वापस से उसी फॉर्म में आ जाती है जिसमें वो मिली होती है.
Okay, so you mean to say that which is able to replenish on its own, if I'm right. Am I right, madam?
Yes, sir. Yes, sir.
Yeah, okay. Any other answers on renewable sources? Because people will normally tell it as continuous source of energy or a perennial source of energy. Like, one basic thing what we people have to understand is that as you people, as some of you would be aware, like sun has a definite life. Sun has a definite life. So normally people were defining it as all those energy resources which will be available continuously, perennial availability. That is a myth, like even sun has a life like. So people are defining renewable energy sources now as the source which remains as source. Let me put it like this, it becomes easier for us to follow. The energy resources in which the source remains as source. Okay, now let me explain it, it becomes easier. If we take wind energy, for example, the high velocity of wind energy, we'll be able to tap it in a windmill, we'll be able to harness it, and we'll be able to generate the output power. Kinetic energy that is available gets converted into electrical energy over here. The wind, whatever that is available, the wind remains as such, like the source remains as source. Likewise, if we take a hydroelectric power plant, hydroelectric power plant, the water remains as water. We don't change the water shape or size as such, like the source will remain as source. If we take conventional fuels, for example, if at all we take coal after exploitation or after getting burnt, it gets converted into ash. Likewise, petrol, if at all we take, it gets converted into flue gas. Clear? So all those energy resources in which the source remains as source, they are called as renewable energy resources. Okay. Now coming back to our area, biomass, whether biomass is renewable, this is one point what people always address, like to some extent biomass is considered as renewable, because if at all we take coal, if at all we take this petrol, this has a definite lifespan. Rather, you have a known quantity which is being explored. After some interval of time, it gets definitely exhausted. Whereas this one, you will be able to grow. You will be able to grow. Once when I cut a tree, the tree will be able to grow again. So in that concept, people are able to classify, or people are able to group this one under renewable energy resource, because though the source gets altered, though the source gets altered, because once when you burn, it gets converted into ash like. But the wood, after you harvest it, it will be able to grow again. In that aspect, people are including it under renewable energy resource. So biomass is included under renewable energy resource. Okay. Now the fourth important question, of late, approximately for the past 20 years or 2 decades or so, more amount of focus is on biomass. The focus is shifted towards biomass. Any idea why we are hovering around this energy resource, biomass? What is the need for us to go behind this one, biomass?
No cost availability, sir.
Yeah, superb. Low cost availability. Low cost availability. Let me tell it with two examples because it becomes much interesting and interactive. In fact, you will be quite surprised and quite shocked also. What is the reason for us to go for this one, this resource? Like, first we'll take two examples. First one, we will take biomass for thermal applications. Second one, biomass for electricity applications, like electrical energy. Okay. For thermal applications, now see, the only factor what makes this biomass, some of them address it as environmentally benign source, it is eco-friendly, all those things and all, those are secondary as such. The factor which drives the industry is also subsidy would be given to promote it, but beyond some interval of time, subsidy will not help. The only factor which helps these renewable energy things to adapt, to be adapted by industry, is that they are economical. We will see how it is economical with two live case studies. First one, in thermal energy, how it becomes economical. Second, in electrical energy, how it becomes economical. Thermal energy, first we will take the common example. We'll take our LPG cook stove, whatever we use in our house, like. Okay. What is the efficiency of this LPG stove? Any approximate idea? What is the typical efficiency levels in which we'll be able to operate? Beta tests are being done, like, so that we'll be able to have it done, and there are high efficiency LPG burners also available. But what will be the typical efficiency range of the LPG cook stove what we have in our house? The answer is null. So probably we'll take 60%. 60%. Okay. Now this first one people were not able to answer. Second one, I think you will be able to answer. What will be the cost of an LPG cylinder?
₹950, sir.
950 rupees. Okay. So let me take it as 1000 rupees approximately. For how many kgs, sir? What is the weight of the LPG cylinder?
14 kg.
14.2 would be the net weight. 14.2 would be the net weight for a domestic LPG cylinder, and this cost is subsidized one. Subsidized one, it will be approximately 1000 rupees for every kg. Sorry, for every cylinder, which is 14.2 kgs. Like, if you go for commercial cylinders, what there is available in hotels as such, subsidized rate is so much. If you go for commercial things and all, the present rate is approximately 2200 rupees for a commercial cylinder, which is 19 kgs of weight. Which is 19 kgs of weight. Okay, so this works out to approximately rupees. Let me go for Y approximations. We'll go for the actual fact itself. So 2200 for 19 kg commercial cylinder. The cost is 115 rupees approximately. Sorry, accurately. So 115 rupees is the cost per kg of LPG cylinder. Okay. Now, any idea about the calorific value of LPG? Whatever we have. Any idea about the calorific value of LPG? Whatever we people have. The heat content that is being obtained by burning 1 kg of LPG.
No idea, sir.
No idea. So then we'll go for 11,000 kilocalories per kg. See, I use kilocalories because in industrial terms we always go for kilocalorie basis. Like You multiply it with 4.186 kilojoules would be available. So 11,000 kilocalories will be available if we burn 1 kg of LPG. As we people have understood, the conversion efficiency of LPG is 60%. So this multiplied with 0.6, which means 6,600 kilocalories of heat energy I'll be able to get for rupees 115. I think all of you are able to understand. This is for every kg, and 1 kg of LPG is so much, 115. So the cost of heat energy that is obtained from LPG is 6,600 kilocalories will be costing me 115 rupees. For understanding terms, let me make it as for 1,000 kilocalories, how much? 1,000 is 1,000 into 115, this divided by 6,600. That value becomes 17.5 rupees approximately. Rupees 17.5 we spend for generating 1,000 kilocalories of heat energy from LPG as a fuel. This is the first understanding what we people have to know. This is the first understanding what we people have to know. Like, okay. So the same thing if we go for chulha, which uses biomass or wooden logs. We go for second case. We go for second case, which uses biomass based chulha, and in fact, Terry, the Energy and Resources Institute had done exhaustive study on this area, and they have gone for improved chulha. Like the efficiency of the improved chulha has been improved, has been doubled almost. You can have it as approximately 20%. The chulhas, whatever that is being used by almost 60% of Indians, the efficiency will be approximately 20% as such. Like chulha per se, the conventional ones, what that was available, the efficiency was around 8 to 10%. Improved chulha wise, we were able to improve the efficiency to this level. Okay. The cost of wood, if at all we take, any approximate values that you people have, what will be the cost of 1 kg of wood, firewood? Village areas, it will be free, but for analysis purposes, we will assume that it is rupees 5 per kg. For agro industries and all, if at all they have, if at all we use boilers, firewood for these things will be obtained at 5,000 rupees a ton. So I'm having the almost same amount over here. The cost of firewood will be approximately rupees 5 per kg. Okay. Calorific value of firewood, if at all we take, any idea? Calorific value, how much it will be?
4,000.
Superb. So we take 4,000 kilocalories as the heat energy that could be obtained from 1 kg of firewood. 4,000 kilocalories of heat energy obtained from 1 kg of firewood. So the conversion, accounting this conversion efficiency over here, 4,000 multiplied with 0.2 is equal to rupees 5. So this is nothing but I'll be able to get 800 kilocalories at the rate of rupees 5. I'll be able to get 8,000 kilocalories at the rate of rupees 5. As usual, for understanding purposes, we will go for 1,000 kilocalorie basis. So 1,000 kilocalories is nothing but 5,000 by 800. 5 multiplied with 1,000, 5,000, this divided by 800. 5,000 divided by 800, 6.25. Rupees 6 rupees 25 paise is the cost for generating 1,000 kilocalories of energy from wood. Whereas if I go for LPG, the cost what we spend is approximately 3 times more, 17.5 rupees. 17.5 rupees. Hence, we depend on biomass. Again, there is one more aspect what I wanted to inform. Thermodynamically, we people have the attention or attraction towards efficiency. We always choose the items whose efficiency will be more, like the more the efficient, the more advantageous it will be, like. But here, efficiency of the LPG stove is so much. Efficiency of chulha, whatever we use, is 1/3 of it. But irrespective of its ineffectiveness or inefficiency, still the cost wise, you can see this is 1/3 of the cost, whatever we have it from LPG. This is the first reason why people prefer biomass for having their thermal energy demands. Likewise, if at all you take for steam generation also, the cost of steam, whatever you have from furnace oil, it will be almost 5 times or 8 times higher as compared to the same steam which is being obtained from wood. Cost of steam, whatever that is being generated from FO, furnace oil, will be approximately 5 to 10 times greater than the steam whatever we have from wood. Hence, industry uses wood-based boilers. This is case one. Why we go for this as an energy resource? Okay. Now we go for another one, electricity. So first one we have seen why we go for biomass on the thermal front. Next we see on electrical front why we go for this on electrical side also. Electrical, we'll compare two things under Mari. One, we will go for diesel based power plant. Second one, we go in for gasifier based power plant. Okay, though this is not my area, but I'll be able to just hint you on the economical aspect. It becomes easier for you people to follow. Okay. Any approximate idea what will be the cost of power, whatever we have it from this one, rupees per kilowatt hour? Any approximate idea what will be the cost for 1 unit of electricity, whatever we have it from diesel? Okay, so next, having no other way, we will derive it. It becomes easier for us to follow. As we all know, efficiency of a diesel power plant will be output by input. Output is 1 unit of electricity. Input is how much amount of fuel I gave into CV of that fuel, calorific value of the fuel. Efficiency of these diesel-based power plants, as we people are aware, it will be the highest among all the cycles. It will be approximately 0.4, 40%. 1 kilowatt hour, I think you would be aware, 1 kilowatt hour is equal to 860 kilocalories. Okay, so substituting all these things and all, this divided by MF, we do not know. Calorific value of diesel, 10,200 kilocalories per kg. So 0.4 is there, 860. So I have this term, I have this term, I have this term. From this one, I'll be able to establish what is the quantity of diesel, kgs of diesel that is required for generating 1 unit of electricity. That could be obtained as 860 by 0.4 multiplied with 10,200. That could be obtained as with this one. So having the same thing like 860 divided by, you don't have a bracket open. Okay, this is standard one. Well, go. Okay, anyway. So 0.4 multiplied with 10,200, 4080, 860 divided by 4080. So the amount of diesel, what that is required for generating 1 unit of electricity is 0.210 kgs or 210 grams of diesel is required for generating 1 unit of electricity. 210 grams of diesel is required for generating 1 unit of electricity. Okay, what is the cost of diesel available on the market? What is the cost of diesel available on the market?
92 per liter.
Rupees 92 per liter. We will take approximately rupees 90 per liter. Okay. The cost of diesel, what that is available in the market, is approximately rupees 90 per liter. But here I have grams. So I have to convert this one into ml. So now how do I convert this grams into ml? How do I convert liters into kgs?
Divide by density.
Okay, divide by specific gravity. We have the value as 0.8 approximately. 0.8 approximately. So once when you have 0.210, this divided by 0.8, if at all I take, 210 grams, that divided by 0.8, which will be 262.5. So have it as approximately 260 ml of diesel is required for generating 1 unit of electricity. As we have understood, 1000 ml cost me ₹90. So 260 ml cost me how much? Again, applying the same direct proportions, 260 multiplied with 90, this divided by 1000. The cost for generating 1 unit of electricity via diesel is ₹23.40 for generating 1 unit of electricity. Again, to stress more, this cost is only the fuel cost. Apart from this, there are other costs what you people would be aware, like maintenance cost would be there, lube oil cost would be there, operating manpower cost would be there, interest on investment would be there. There are several other aspects, like the fuel cost alone will be working around ₹23.5 for generating 1 unit of electricity from diesel power plant. If you go for wood-based power plants, gasifier you can take, or even we can go for combustion mode also. The logic would be, say, the efficiency would be by a factor of 0.3. It will be lower. Rankine cycle power plants, efficiency will be around 30% approximately. Calorific value of wood, it gets altered. As was informed, it will be 4000 kilocalories per kg. So you know these two values, from that accordingly you can have it done. Like probably if at all we do it, okay, now let me try to do that one also. The kgs of wood, what that has to be supplied. Kgs of firewood, what that is required for generating 1 unit of electricity, that will be 860 multiplied by 0.3 into 4000. 0.3 multiplied with 4000. 860 divided by 1200. So approximately 0.7 kg of firewood is required. 0.7 kgs of firewood is required. This multiplied with ₹5 per kg will be able to have it as ₹3.5 per kilowatt hour. Just compare the cost of power, whatever you get from an biomass based power plant with that of a diesel based power plant. But again, if you go for coal, the value will be almost same. If you go for coal, the value will be almost same. Like, but I'm comparing with an diesel power plant, so that it becomes easier for us to understand the economic aspect of it. Like, so the cost of power from a diesel power plant will be approximately ₹23.5, whereas from a biomass based power plant will be ₹3.5. This is a factor which drives our attention towards this resource. Like, so biomass is being preferred for its cost effectiveness as compared to conventional fuels. Okay. Apart from this, people also tell it as eco-friendly. Apart from this, people also inform it as eco-friendly. There is also one more tag what people attach it to it. It is carbon neutral. It is carbon neutral. The concept wise, what they tell is that the carbon that is available in the fuel, upon oxidation, it will form carbon dioxide plus abundant amount of heat energy. This heat energy will be able to harness, will be able to have it converted into other forms. Like, so once when the wood is getting burnt, the CO2 would be obtained, true. But again, the CO2 plus water, whatever we have it across, plus sunlight, photosynthesis process happens. This gets converted into C6H12O6 starch. This CO2, whatever the plant has emitted, once when it has got burnt, it will be reabsorbed back. Hence, it is called as carbon neutral. This biomass is also regarded as carbon neutral technique, like carbon neutral resource. Like, okay, so the fourth aspect is over. Fifth aspect, is it available to us? Like, any approximate idea how much amount of biomass is generated in India per annum? Our institute, Anna University, was one of the apex institute of MNRE, Ministry of New and Renewable Energy. We have done the biomass assessment for 4 different states of India. Likewise, there were other apex institute also. Accordingly, we were able to establish the quantity of these resources available per annum. As per the latest information, approximately 700 million tons are available every year. As per the latest information, 700 million tons of these wastes are available per year, availability wise. Surplus wise, you can take approximately 200 to 300 million tons of these things are available as surplus, as untapped resources. Approximately 300 million tons of these resources are available as excess per annum in India. Okay. Now comes the last option. So all these things are the basic informations. Now comes the last one, conversion mechanisms. Probably this is the one where we have to work around. Now, the conversion mechanisms, what are the various mechanisms through which we'll be able to convert the biomass into energy? Bioenergy conversion techniques, BECT, biomass to energy conversion techniques. Like broadly, this has been classified into three major types. Broadly, this is being converted into or grouped under three major types. First is called as physiochemical. Second is called as biochemical. Third one is called as thermochemical, where our focus would be. Okay. Physiochemical wise, you people would be aware. The examples for physiochemicals are briquetting, where we'll be able to convert the loose biomass into one densified one. Biodiesel extraction. We crush them, then transesterification we adopt. Automatically, we'll be able to have this one obtained. From this one, we'll be able to operate the engines as such. So these two techniques, apart from this, there are other things also. These two techniques will be available. These two techniques are examples of the first one. Biochemical wise, different techniques are available. Among them, biomethanation is an example, where we will be able to convert it into one methane rich gas. Biomass is getting converted into one gas which will be richer in methane. Approximately 70% will be able to have methane. And apart from this, composting is another example. There are other aspects like, in fact, alcohol, whatever we generate, is also another example. Microorganisms will be having a role, like, and algae also will be included under this route, like biochemical methods through which we'll be able to convert these organic matter into one useful product. Like thermochemical is the one where we people see. Thermochemical, there are four broad techniques. With the help of heat, we'll be able to break down, then accordingly we'll be able to harness energy from them. The first technique is called as combustion. Second technique, gasification. Third technique, pyrolysis. Fourth technique, the technique what I'll be teaching you now, what I'll be handling you now, it is carbonization. These are the four major routes through which we'll be able to convert a woody biomass into one useful energy generating resource. Okay. Combustion. Now again, these four techniques are classified with only one parameter, which is called as equivalence ratio. These four techniques are classified with only one technical parameter. It is called as equivalence ratio. We will see what basically that equivalence ratio means. Any idea about this equivalence ratio? What basically is this equivalence ratio? Any inputs? Okay. The equivalence ratio.
1 by lambda, sir.
1 by lambda, 1 by lambda, 1 by lambda. Okay, now let me put it in another way. It becomes easier for you people to follow. Like actual air, whatever I have supplied by stoichiometric air. Actual air, whatever I have supplied as compared to stoichiometric air. This is what we call it as equivalence ratio. Equivalence ratio. Okay. What do we mean by this actual air? What do we mean by the stoichiometric air? First, we will understand about the stoichiometric air. Then it becomes easier for us to understand about actual air. Then the equivalence ratio also. Now, what do we mean by stoichiometric air? Answers, please. What do you mean by stoichiometry or stoichiometric air?
Minimum amount of gas for combustion.
Superb, sir. Superb, sir. So this is the chemically balanced air. We balance the ultimate analysis. Rather, we do ultimate analysis. We arrive at the elements and we estimate the quantity of air what that is required for completely burning the fuel. This is chemically balanced amount of air. This is one way of having it informed. Second one, this is also the theoretical air what that is required so that we'll be able to ensure that all parts of the fuel is getting completely burnt. So this is the chemically balanced amount of air or theoretical air or ideal air what that has to be supplied so that we'll be able to completely burn the fuel. So that we'll be able to have the fuel 100% burnt. Okay. Now let us assume for easy understanding purpose our fuel contains only carbon. We will assume I have a fuel which contains 100% carbon. Diamond and Tamari, we will be able to take an example. I have 1 kg of carbon. How do I estimate the amount of air what that has to be supplied? So we all are aware about the general equation, carbon plus oxygen, it will form carbon dioxide. Molecular weights, if at all we substitute and if we do analysis like 12 kgs of carbon requires 32 kgs of oxygen to form 44 kgs of CO2. Okay, so again the basis wise 12 kg of carbon requires 32 kgs of oxygen. So 1 kg of carbon requires how much kgs of oxygen? So 32 by 12, this is nothing but 2 divided by 12, 2.67. So if at all I need to burn a fuel which contains 100% carbon, the amount of air what that has to be supplied is 2.67 kgs of oxygen has to be supplied for 1 kg of fuel which contains 100% carbon. 2.67. 2.67. Okay. Now again, one more aspect. See, we are interested in air, not oxygen. We are interested in air, not oxygen. So how do I convert this oxygen into air? As we people are aware, the atmospheric air contains different constituents. The highest among those things are, any idea? What are the constituents of atmospheric air? Nitrogen is highest, then we'll have oxygen, then we have argon, then we'll be having CO2, water vapor. For stoichiometry analysis, what we do is that we assume that these components aren't there. We assume that these components aren't there and we take only N2 and O2 alone. By volume basis and by weight basis, oxygen is taken as 21 and 23. Remaining is taken as nitrogen, 79 and 77. So in other words, 21 cubic meter of oxygen will make 100 cubic meter of air. 23 kgs of oxygen will make 100 kgs of air. Okay, but so likewise here, to see as we people have seen, this is kgs of oxygen, right? So 23 kgs of oxygen makes 100 kgs of air. So 2.67 kgs of oxygen makes how much kgs of air? As we people are aware, 2.67 into 100 by 23. 2.67 multiplied with 100. This divided by 23. 11.6. So the stoichiometric air, what that has to be supplied is 11.6 kgs of air for my fuel, which contains 100% of carbon. This air, whatever we people have established. So now, as you people would have seen, like the stoichiometric air for the fuel which contains 100% carbon is 11.6. Is 11.6. This is stoichiometric air. This is stoichiometric air. Now again, I have assumed the fuel contains only carbon alone. If the fuel contains carbon, the ultimate analysis we do and we estimate the elemental composition as carbon, hydrogen, oxygen, nitrogen, sulfur. We inform it as cons. So based on these elements, we'll be accounting and then accordingly we'll be able to establish this much amount of air is required. The process, whatever we have done as of now, that is called a stoichiometry, and this air, whatever we have estimated, this is called a stoichiometric air or chemically balanced air, what that is required for having the fuel to get burnt 100%. Okay. Now the actual air, whatever we supply, will be the stoichiometric air, whatever that has been established as of now, plus some amount of air as excess. We'll be sending some amount of air as excess. Okay. The stoichiometric air we have estimated as approximately 12, which is approximately 12. We'll be sending approximately 4 kgs of air as excess, so it becomes 16 kgs of air. We'll be sending approximately, and this 4 is decided based on the fuel. If it is LPG, the amount of excess air will be too low. If it is oil, atomized oil, the excess air will be lower. If it is wood, surface area will be lower. Automatically, the amount of air, whatever we send as excess, will be more like. So the excess air is influenced by different parameters. One among them is the surface area of the fuel. Okay. So this is the actual amount of air, whatever that has been sent. Stoichiometric air of air, we have established it as 12. Now we define equivalence ratio as actual amount of air, whatever we have sent, as compared to the SA, stoichiometric amount of air. If it is 16 by 12, if it is more than 1, those thermochemical roots are called under one term, that is called as combustion. This is the first root. This is the first root where equivalence ratio we will be maintaining more than 1. More than or equal to 1. Equal to is a very rare case which we never do. Like combustion is the first technique through which we'll be able to burn the wood. We'll be able to have abundant amount of heat energy. Let me be very precise again. We were taking carbon plus oxygen. It will give CO2 plus abundant amount of heat energy. This is an exothermic process. Approximately this will be 8,800 kilocalories of heat energy that will be obtained for every kg of carbon. 8,800 kilocalories of heat energy would be obtained for every kg of carbon. Okay, this is the first root. Second root is called as gasification root. And here, the equivalence ratio will be maintained as 0.3. Here, the equivalence ratio will be maintained as 0.3. What it means is that, as we people have understood earlier, for a fuel, or for the fuel what we have taken, 12 kg of air has to be supplied so that the fuel would get completely burned. The fuel would get completely oxidized. It will be able to give abundant amount of heat energy what it has to. But if I don't give the required amount of air, and if I lower it, and if I maintain an equivalence ratio of 0.3, that is, rather than supplying 12, I'll be supplying 12 into 0.3, I'll be supplying only 4. I'll be supplying 4. In that case, the equivalence ratio will be actual air, whatever we have sent as 4 as compared to 12, the equivalence ratio will be 0.3. If I do that one, the solid fuel gets converted into one burnable gas. The solid fuel gets converted into one burnable gas. There are different concepts. Again, people will be able to explain it to you. My other speakers will be able to explain it to you on this aspect. Like the basic aspect is that carbon that is available inside the fuel plus oxygen, whatever you gave, it gets converted into CO2 plus heat energy. This always happens. Since the amount of air, whatever you have supplied, is lower, the carbon dioxide, whatever that has got formed, plus the fuel, whatever that is available as unburnt, plus this heat energy, whatever that is there, it will be happening. An endothermic process will happen. It gets converted into 2CO. Hence, you are able to convert a solid fuel into one burnable gas. The solid fuel, whatever you have it over here, it gets converted into one burnable gas. That is called as this technique, gasification. The third technique, it is called as pyrolysis. The same concept here, the equivalence ratio will be maintained as 0.1. Simple concept. Equivalence ratio will be maintained as 0.1. That is, rather, we don't even send 4 kgs of air. We'll be sending in just 1.2 kgs of air. Rather than sending 4 kgs of air, we'll be sending only 1.2 kgs of air as against 12. Equivalence ratio will be approximately 0.1. Among the techniques, I prefer this technique more because this gives me the liberty to choose what type of product I can have. I can have solid, I can have liquid, I can have gas. Based on the operating parameters, based on how I control the environment, I'll be able to increase the yield of solid, that is char, or even I can have more amount of tar, even I can have higher amount of gas also. But pyrolysis will be able to give me these three outputs. I'll be able to have solid output, I'll be able to have liquid output, I'll also be able to have gaseous output. Pyrolysis, equivalence ratio will be maintained as 0.1. The last technique, what I have to handle for this day's session, it is carbonization, because the basics have to be taught so that advancement becomes easier. Here, the equivalence ratio will be zilch. Rather, we don't supply any air externally. Rather, we don't supply any air externally. It will be less than 0.5. It will be less than 0.5. The oxygen available inherently in the fuel. The oxygen available inherently in the fuel will be taken into account, and some oxygen that was available in the voids of the wood would be taken, and will be able to convert the solid biomass into charcoal. This is what we mean as carbonization. Any doubts as of now? Any doubts as of now?
No, sir.
No. These are the 6 broad things and all. Only with these 6 broad mechanisms, you will be able to understand what basically it is. Now we will compare biomass versus coal. Now we will compare. Now this is hiding. Okay, done. Again, adjacent 5 slides, it becomes easier for you to comprehend on what way this is comparing with coal. The first parameter, what we'll be comparing is the bulk density. Coal will be more, approximately 650 to 850 kgs for every cubic meter. And again, this is the range. There are some things which will be having very low values. There are some which will be having very high values. This is the typical operating range of the fuel like biomass like. And if we divide the average between these two, it is approximately 5. Now, what do you understand by this 5? Bulk density of these agro residues would be 1/5 of coal. Now, what do you understand from this? Bulk density wise. Bulk density will be lower. So, in what way it will affect the operation of the industry or the plant?
Combustion rate, sir.
Combustion rate, to some extent, yes, it is true. The 2 major aspects in which it will affect is transportation cost. 1 lorry load of coal for the same weight will be equal to 5 lorry loads of wood for the same weight. So the transportation cost would be more. This is case 1. The storage space also will be more. The storage, the yard space requirement also will be more. And as was informed earlier by another participant, combustion wise, the furnace chamber will be bulky as compared to coal. Moisture content wise, if at all you see, the moisture content of coal will be approximately 5 to 10%. Again, if it is anthracite coal, it will be 5. If we go for lignite, it will be around 30% also. Okay. Now, biomass wise, if at all you see, it will be hovering between 15 to 40. It will be hovering between 15 to 40. This is a negative point as far as the agro waste goes, like, because if it is higher, moisture content, if it is higher, combustion becomes very tough. Drying has to be done, like the calorific value of the fuel would be lower. Of late, we have seen on the market what people use for having these woods for their industries. They have instantaneous moisture meters, probably. Yeah. These woods, what they have is that they have an instantaneous moisture meter. The moisture meter will be having 2 nail-like options. This is, and it will be able to inform the instantaneous value, moisture content value. They'll be hitting this one onto this wood like, and it will be able to immediately inform what will be the moisture content in the wood like. The cost of these wood would be fixed. Of late, the cost of these wood are being fixed based on the moisture content that is available inside the wood like. Okay. Calorific value wise, yes, of course, it will be, we cannot tell that it will be surpassing coal, but we can tell that it will be able to match that of coal, or it is equal to that of coal. Coconut shell will be able to match. Coconut shell will be able to match. Bagasse, after drying, it will be able to match. Paddy hay will be able to match. So Again, there are other residues which will be quite lower value, but we cannot tell it as equal, but we can tell it as equivalent, like ash content. This is one important factor, the boon and bane of Indian coal. It is what normally I tell to my ME students, like boon and bane of Indian coal. There is one major advantage of Indian coal. The advantage of Indian coal is that the sulfur content in Indian coal as compared to imported Indonesian or Australian coals are lower. So the sulfuric acid will be lower. Flue gas desulfurization, what we do at the flue gas side, will become lower. Rather, we can avoid it. The bane of Indian coal is that it contains approximately 40% ash. The bane of Indian coal is that it contains approximately 40% ash. Let me put it in another way, it becomes easier. If you purchase 100 kg rice bag, and if that rice bag contains 40 kgs of stone, it will be annoyed, right? Likewise, the unburns in Indian coal will be approximately 30 to 40%. Like. Okay, now on the ash content wise, biomass, if at all you take, will be quite shocked. The ash content will be hovering between 3 to 5% for maximum things. Only for rice husk, this value will be very high. Only for select few values, it will be very high. Like, but wood, if at all you take, the ash content will be hovering at this value. Like, so this is the typical value of ash, whatever we'll be having in wood, as compared to 30 to 40% of ash, whatever we have in coal. Just see the amount of ash, whatever we have between these two. Volatile matters wise, biomass contains more volatile matter. Probably you will be able to see the volatile matter. Volatile matter means these are long chain, low boiling hydrocarbons. Volatile matters, to be very precise, these are long chain, low boiling hydrocarbons. If at all you burn coal, you'll be able to see some red flashes which occurs in the coal burning. Like, all those are called as volatile matters. They escape out immediately. Like, see, I have used the LPG burner as an example, and I have used wood burning as an example. Volatile matter in wood is more. As a result, the plume length or the flame length will be much higher. The flame length will be much higher. Whereas in case of LPG, the flame length will be much lower because volatile matter comparatively it will be lower. Clear? Volatile matter is more in case of agricultural waste. Like, okay. So now we have understood the basics about all these things and all. Now we go on to the topic in which I have to address you upon. Carbonization. Carbonization. Okay. Any idea what basically it means? Any idea what basically it means, like carbonization? I have handled you now.
Making it more combustible, sir.
Yeah, we maintain an equivalence ratio of 0 approximately. We thermally degrade, and we convert wood into charcoal. We thermally degrade and we convert wood into charcoal. The conversion process through which we'll be able to make charcoal from wood is called as carbonization, or coal getting converted into coke, or lignite getting converted into LiCO. These are examples of carbonization process. These are examples for carbonization process. Let me tell it with an example, it becomes easier. Let me tell it this, it becomes easier. One logic what we people have to understand is, assume that a diabetic person comes to your home, you serve him a cup of coffee. You serve him a cup of coffee. This is the coffee, whatever you have served. He tells the sugar content in your cup of coffee is more. Sugar content is more is what he tells. Like, so what do you do to lower this one sugar content? What are the options, avenues available for having this one lowered?
Increase the water.
One is suppose if you don't like him, you can add water. That is good. Okay. Apart from that, so first one we dilute it with water. First one we dilute it with milk. Yeah, super. So if you like him more, you'll be adding milk, and if you don't like him, probably you'll be doing these two options like water and milk. But one basic thing what we people have to understand now, if you add milk or if you add water, the content of coffee becomes like this, it becomes higher, like, okay. But one basic thing what the person who drinks coffee has to understand is that the quantity of sugar, whatever that was there, remains same. One basic thing, whatever that person who drinks the coffee has to understand that the quantity of sugar becomes same, we just dilute it. Likewise, in carbonization also, we remove moisture and other undesirables. As a result, the carbon content what that was available in the wood gets enhanced. Carbon content based on the weight wise it will be same, but percentage wise it will become more. Then thermally we'll be heating it out and we'll be able to remove these cellulose component, hemicellulose component from the wood. Cellulose, again, if we do the proximate analysis of wood, again, there are two types of analysis what we normally do. There are two analysis whatever we do for characterizing any fuel. One is called as proximate analysis, second is called as ultimate analysis. In case of this one, proximate analysis, first one, moisture content will be established, volatile matter will be established, ash will be established, 100 minus 1 plus 2 plus 3 will be able to have fixed carbon. In case of ultimate analysis, which we also refer as elemental analysis, we'll be able to have carbon, hydrogen, oxygen, nitrogen, sulfur. We do these two analysis for different purposes. Ultimate analysis, as you people would have understood, this is being made just to establish what is the stoichiometric air what there has to be supplied. What is the amount of air what that I have to supply so that I will be able to completely convert this fuel into heat energy. That is one. Second, if the fuel contains more amount of sulfur, flue gas desulfurization has to be done. So what is the capacity of that plant has to be done only with this analysis. This is the need for doing ultimate analysis, or also called as elemental analysis. In case of proximate analysis, we do these things are all moisture content, volatile matter, ash, and this FC. Here, we try to remove the moisture content that it was available, volatile matter that was available. As a result, the ash content and fixed carbon content that is available inside the fuel gets increased. Okay, now let me put it with example. It becomes easier with numbers. It becomes easier. Assume that moisture content was 30%. I'll use some other color. It becomes easier also. Red color I'll take. Like moisture content initially was 30%. Volatile matter, assume it as 40%. Ash was say 5%. 75. Fixed carbon was 25. This was for the initial raw wood what I was having it across. By somehow, I am able to remove these two constituents from the wood. For every 100 kg of wood, these were the constituents what there was available earlier. But now, by some option, I am able to drive these two things off. So the residue what I'll be having is 5 and 25, so it will make 30. So percentage wise, if you see, fixed carbon will be 25 out of 30. So percentage wise, if at all you see, it will be 25 out of 30. By 6, it will be 83%. So this has become, just understand the carbon what that was 25% earlier, the carbon what that was 25% in the wood earlier had become 83% now by driving off the undesirables from the wood. This is what we call it as carbonization process, and this carbonization process will be maintained at an equivalence ratio of approximately lesser than 0.1. We don't give any oxygen at all. With the oxygen what that was available inherently in the fuel, it will be able to have it done. Okay, and what we do is that we drive off these aspects. The lignin gets charred, automatically we'll be able to have it done. Just understand these are the temperature ranges in which these three things will go off. So carbonization will effectively start once when the temperature is approximately around 300 degrees centigrade. We char it. To be very precise, we char it, we roast it. As a result, we'll be able to drive off all these aspects. As a result, the carbon content that is available inside the wood gets enhanced, which we call it as charcoal. Okay. Charcoal characteristics. Before we go in for these charcoal characteristics and all, we will see the image how a charcoal will look like. This is how typically a wooden log will look like, and this is how a charcoal will look like. Now comes the basics. Why we need to have charcoal? What are the various applications of charcoal? Any answers, please? What is the need for us? Or else rather, you just inform me the applications of this one. What are the applications of charcoal?
Absorber.
First one, it's a wood absorbent. It will be able to retain moisture. And this application you people would have seen, like in our houses and all, the earth rods, whatever we place, in the electrical mains of residential buildings, commercial buildings, industries and all, you will be adding salt plus charcoal. You will be able to add salt plus charcoal, and here you will be able to see that this is a bad conductor of heat and electricity. This is a bad conductor of heat and electricity, but unfortunately, I add this charcoal for the earth rods. Any idea why? Why we add the salt plus charcoal for the earth rods, whatever that is being installed in the electrical mains?
In order to avoid transfer of electricity.
No. Earth rods, it has to transfer electricity. Earth rods, the resistance of the earth rods, it has to be lower. The resistance of these earth rods has to be lower as compared to the resistance offered by us humans. Only then current will always follow the least resistance path. If at all there is any electrical shock, it will be vented out through the earth rods. Like the salt, whatever we add, it's an electrolyte. Conductivity will be enhanced. The answer was informed earlier. It's a very good absorbent. Moisture will be retained by these charcoal. On the earth rod, the charcoal will facilitate of retaining moisture. The salt, whatever you add, it will facilitate conductivity. As a result, resistance offered by the earth rod will be lower as compared to us. As a result, current shock would be lower to us. So this is one application. So it's a good absorbent. First one. Second application.
Silencer for harmful heaters.
Sir, please, sir.
Silencer, through the silencer.
Through the silencer, I haven't come across, sir. I do not know where in the silencers it is being used.
It is already used, sir, but for capturing the carbon, exhaust the carbon.
For capturing the carbon. Okay. Probably I do not know. I'm not aware. Let me have it obtained. And another in all our RO plants, whatever we have in our house, also activated carbon would be there. Like it is a deodorant. It will be able to have other applications also. That is second application. Apart from this, one major application or two major applications, what we would have encountered in day-to-day applications. Daily, we would be able to see that one. Two applications we will see daily, 2 or 3 also.
Used as a fuel.
It is used as a fuel. Yes, sir. Of course. Where, sir? Where it is being preferred? True. Where it is being preferred. One common area where it is being always opted for. The dry cleaning. The dry cleaning shops, you will be able to see the Iron Man having these charcoals, right?
Iron Man has that, sir.
Yeah. Okay. Now comes a basic question. Yeah. Why he uses charcoal? Why not he use wood? What is the necessity for him to use charcoal as compared to wooden pieces?
Volatile matter is has been removed.
Yeah, volatile matter has been removed. As a result, the smokeless combustion will happen. It is true. Excellent answer. Apart from that one, it will be light in weight. Third one, calorific value will be higher. And again, there was also another answer. It will burn very slowly. Volatile matter has been removed, so it will burn very slowly. So once when he starts in the morning, the heat will be available till evening. So that's the advantage why he goes for charcoal. And barbecues, probably you people would have seen, like where people also use this one. the advantages, whatever that was informed earlier, all those things are applicable even now. It will be able to burn slowly. It will be able to give abundant amount of heat energy. It won't. It will burn without any smokes. Like, so, these are the advantages. Like, okay, these are the advantages. Now, what is the cost of this wood, which we have seen approximately? The cost of wood is approximately 5 rupees per kg. What is the cost of this one? Charcoal?
Approximately 25 per kg, sir.
Ah, super. 25 to 30 rupees is the one. Again, the price will go as high as 40 rupees also. For those carbon, for those charcoals whose iodine value is higher, that will be for activated carbon. That value will be even higher than this. But charcoal, whatever you have in the market, it will be between rupees 25 to 40. Approximately 5 times you can have it across. Approximately 5 times will be the higher cost of this one. Okay, this is one. Calorific value wise, it will become double. Calorific value, this we have seen as approximately 4,000 kilocalories per kg. Whereas here, this will be approximately 7,000 to 8,000 kilocalories per kg. It will become double. Okay, now yield wise, how much would be the yield? Any approximate idea? 100 kg of wood gives how much kgs of charcoal? 30 kgs. 30% would be the typical yield. Probably I'll be able to show you some examples also. It becomes easier for you people to understand also. 100 kg of wood would typically get converted into 30 kgs of charcoal. Now we will see the cost factor. 100 kg of wood, if at all I do, it will be 500 rupees. I have to shell out. 30 kg of charcoal, 30. If I take approximately 30 rupees is the cost, it will become rupees 900. Okay. 900 rupees is the value. So this becomes double. The cost wise, it becomes double. If I convert wood into charcoal, this is a money spinning venture for me. I'll be able to get double the profit. I'll be able to get double the profit. Okay. The advantages we have informed already. Okay. Now we will see the characteristics of it. Like, it is jet black. Bad conductor we have seen already. Again, a good quality charcoal will be able to shine. It will not crush. The original shape and size of the wood would have been retained. And one important factor, the fingers will not become dirty. If you handle it also, the charcoal will be remaining intact. Your finger will be free from carbon. These are the characteristics of a good quality concrete. And once when you have it in water, it will be able to float in water. And the calorific value wise, as I have informed you, it becomes double as compared to the wood and ramalan. And elemental wise, it will be having all those things, whatever that was available in the wood. But these values will be lower. Hydrogen, oxygen, nitrogen, sulfur will be lower. Carbon content and ash will be enhanced as compared to the raw wood. Like, fixed carbon content will be more than 70%. That's the advantage of it. Like, an ignition temperature, it is very easier for me to ignite because moisture content would be lower. Pollution wise, it will be lower. These are the characteristics of a good quality charcoal. Okay. These are the different standards what we people adopt for doing the proximate and ultimate analysis. These are the different standards what we people adopt in the lab for estimating the proximate and ultimate analysis. The first column indicates the proximate analysis for wood. The second column indicates the proximate analysis for charcoal. You can see how the moisture content had become lower. 15% was there for every 100 kg, 15 kgs would have been there. Now it has become lower, just 2 to 4. We have driven off these two, volatile matter and moisture. Volatile matter and moisture has been driven off. As a result, this value would have come down. This value would have come down. These two values would have gone up. The fixed carbon would have become almost 4 times. From 20, it had become 80. This also would have become higher by 4 times, approximately from 2 to 4. As I told you earlier, by driving off the undesirables, we'll be able to improve upon the carbon content what that is available inside the fuel. This is called as carbonization process, for which the equivalence ratio will be almost 0. The inherent oxygen what that was available inside the fuel. Fuel contains 52.1% out of 100 kg of wood. Carbon was only 40%. Oxygen was approximately 52%. Ultimate analysis reveals like 52% of oxygen in it. We use this 52% of oxygen what that was available in the wood, and that value would have become drastically lower, and this carbon would have become much higher. Okay, and some home task for you. If you are interested, you can do this home task. Like fixed carbon, whatever we have from proximate analysis, and the carbon, whatever you have from elemental analysis, will never be the same. Will never be the same, but name wise it is almost identical. Will never be the same, but name wise it will never be. Name wise it will be same, but constituent wise it will not be identical. You can do a home task and you can explore why it is not so. Okay, on the heating value, I had informed you already. The heating value will become double. It is approximately 4,000 kilocalories per kg. This is approximately 7,000 to 8,000 kilocalories per kg. Bulk density wise, this becomes lower. So storage volume, whatever that has to be there, for the same weight, it will be more. Calorific value wise, it is higher. But if at all you are interested in stacking by weight, then the storage volume will be more. Any doubts on this? Proximate and ultimate analysis of wood and charcoal. Okay, no doubts. These are the various factors which influence the carbonization rate and carbonization yield also. Okay, moisture content will be having a definite say. Volatile matter will be able to have a say. Higher the lignin, higher would be the yield, like ash content also. Heating rate, I'll be able to show you an image through how the heating rate, how this RT will play a role. These three factors, you can see how these three factors play a role automatically, how these controls the yield of char, and the other two factors also. This is being obtained from thermochemical characterization of biomass. Author is Dr. PVR Iyer et al. You can have that book. Accordingly, it will be there. I haven't acknowledged it. It has to be acknowledged over there. Okay, now see here. This is the residence time, whatever we have, or the time interval at which we retain at a higher temperature. Like this is the heating rate. I think you people are able to aware. Heating rate is how much kilocalories of heat I have it for every second, for every interval of time. Heating rate, watts, joules per second. Clear? Clear? Okay. And if the heating rate is much higher, and if the residence time, whatever I give is much lower, I'll be able to have more amount of char. See, we can control the amount of gas content, the liquid content, the solid content by controlling these two parameters. One is the time interval at which I have this one, and at what heating rate we are having it done. If my interest is to have more amount of charcoal, then I should go for this one, because beyond this point the yield is same almost. So I can go for this option. Residence time has to be approximately 100 seconds, and the heating rate has to be slower. If it is a process, I'll be able to have more amount of charcoal. If my intention is to have more amount of gas, then the residence time has to be lower. Residence time has to be lower. The heating rate has to be much higher. Like so, by controlling these parameters, we'll be able to alter the amount of charcoal yield, whatever we get. Like okay. Now, let me tell you the conventional charcoal making process. Conventional charcoal process, or how it is being done as of now. This is a case study what we people have done at Ramnad area in down south of India. The conventional charcoal making process is a laborious process. It is labor intensive. It is not environmentally benign. Almost 15 processes has to be done. Almost 15 processes has to be done so that we'll be able to convert this wooden log into charcoal. I'll be able to address all these things around so that it becomes easier for you people to understand. I have images so that it becomes quite interactive, quite interesting also. First one, you need to have this Prosophis juliflora. I'll be able to show you the image of that. It becomes easier for you people to follow. This grows across India, pan India. It is available across India. It grows for all seasons. Even rain or even in shine also, it will be able to grow. Even in drought conditions also, it will be able to grow. After you cut it, it will be transported, it will be bundled, it will be stacked, it will be covered with paddy, straw and wet soil. As a result, the atmospheric air will be prevented to enter. Then it will be ignited. 5 days, as you people would have seen, like for carbonization process, this has to happen slowly. So it will be taking typically 5 days, and cooling will be done after that one. Then you uncar, then you will be able to segregate the char and unburns. Then you repeat the process for unburns. Then automatically all these three are commercial aspects of it, which I will not address now. Now this is what we call it as Prosophis juliflora. This almost all the people would have seen. Like it will be thorny. it is not very easier to handle this one, but it will be growing as a wild bush. Like if you have only one plant, probably after some 2 or 3 years, that whole area will be manifested with this crop. Like okay, and this Prosophis, it's in canopy type, sinuous type. Probably the stem won't be erect trees and all. It won't be having a straight or erect stem. Like it will be twisted always. Flowering begins at a very less age, and it will be greenish color almost. Fragrance will be zilch like, and it will flower twice a year, and it will be having a taproot mechanism. As a result, it will be able to take the water that is available deep inside the soil. These are the different forms of the tree. Approximately 6 forms it will be able to have it. It is almost like an amoeba. Like it can take any shape. Like, and this is the typical root option. Approximately 2 months of time. Approximately 2 months of time, the root would have gone approximately 1.5 feet. 1.5 feet. Okay, now this is the first aspect of it. Now you can see how the Prosophis is available across the area. Like in the barren, uncultivable wastelands, it will be available. In the tank bunds also, it will be available. All these are the areas where you will be able to see abundant amount of these things and all. And they harvest it. And there are 3 types of things that you can have it across. One is twigs. Whatever this person is harvesting, these are the small things. Whatever you have it over here, all these are called as twigs. Like whatever you have over here, all these are called as locks. These are called as locks. These are called as twigs. And once when you uproot this, these are called as roots. So these are the 3 types of raw material what we can expect from them. One is twigs, other is locks, the third one is roots. Roots would be taken occasionally. Majority of the charcoal is being obtained from the locks. The twigs also yields charcoal, but the cost what it fetches will be too low. This is an image of twigs, locks, and roots. So this is the type, raw material what we have, like wood as such, and it will be harvested in one area, rather cut in an area, and it will be transported to an area which is adjacent to the residence of the person who makes this one. The charcoal maker's home will be adjacent to this carbonization process. I'll tell you why. Monitoring has to be done 24/7 for almost 8 days. So, 1 minute, I have a call. Let me cut that. So whatever that was cut at on site, it will be transported to an area which is adjoining his home. Then after that one, they bundle it so that the stacking becomes easier. You will be able to see one pile of carbonization heap, what that has been formed over here, another pile what that is being formed over here. For twigs, they bundle it like this. For twigs alone, they tie it up so that it will not loosen. The carbonization process will happen at ease. And it is how they stack. This is how they stack. This process is being carried out for twigs alone. For twigs alone, they stack it like this after it is being bundled. The bundling will be done so that it will be retaining its original structure. Hence, it will be bundled. This is how we stack for logs. For logs, we need not bundle. Bundling can be avoided because it will be able to stand on its own. Bundling is avoided over here. It can be stacked like this one. It can be able to stand on its own, almost like a pyramid, almost like a human pyramid. Janmashtami, you people would have seen like the same mechanism will be done over here. Okay, now this is a heap like one. And if at all I have to carbonize it, as we people are aware, we have to heat it, right? So once when I give the flame, once when I ignite it over here, the atmospheric air will come in. The wood is available. We have fuel, we have ignition source, we have air. The whole fuel, what that has been agglomerated over here, it will burn immediately. In order to avoid that one, I should have a mechanism through which I have to prevent the air entry. In order to prevent the air entry, as we people are aware, the equivalence ratio has to be maintained approximately 0. The equivalence ratio has to be maintained approximately 0. So in order to prevent the air entry, what we do is that we'll be covering it with paddy hay. Paddy hay is used to give the structural strength, and this paddy hay will be covered with soil. The paddy hay will be laid onto the wooden heaps and it will be covered with an soil that will be wet intentionally. As a result, the surface area will become too less. It becomes difficult for the air to proliferate on the interiors. The air cannot move in. We arrest the air movement inside. So once when those arrangements have been done, now see here, you can see the paddy hay that is available on the top and which has been covered with the wet soil. And what we do in the conventional process is that we ignite some small amount of wood, cloth or all those things and all, and then we have this one inserted over here. Then we have this one closed. This opening also will be closed. So now what you people have to understand is that an heap was available. Onto this heap, we have covered it with paddy hay and wet soil. We had some small openings over here. We had the flame over here. Then we have arrested that opening also. So the oxygen what that was available in the wood and the oxygen that was available in the interstitial areas or the air that was available on the voids, these two will aid the process. The carbonization process will happen very slowly. As I told you earlier, the actual amount of air supply is 0. As the actual amount of air supply is 0, the equivalence ratio is also 0, because equivalence ratio, as we people are aware, it is actual amount of air by SA. Okay, so the equivalence ratio will be 0 here. And once when you do this, the process starts like, and it will be having it done like. After ignition, we have this top hole closed and we make openings here, one on this side, one on this side, one on that side, one on the other side and all. As a result, the burnt products will vent out. As a result, the burnt products, what that is available over here, will vent out. See, once when the combustion happens in the interior and higher pressure will be available, this pressure will force the burnt products to go outside. The atmospheric air will never find enough pressure to go inside. The flue gas alone will be vented out. Okay, after some interval, now see here, he is able to have the holes that is available at the top. All these things are being done. After 2 to 3, okay, again, I was informing you. This process happens after he had made the hole at the top, like monitoring will happen. The person who had stacked will monitor it. It is not like someone stack and other person monitor it, because this is a matter of life and death, like, because in the if it is being stacked improperly, there are chances for this person to move in also, cave in. It might happen, or it had happened also. So normally the person who stacks will be able to see all these things in Ramari, and he'll be able to monitor it 24/7 for approximately 5 days. Hence, this will be located adjacent to his home. Suppose if monitoring is not happening, the wet soil, whatever we have applied on the top, will become dry because of high temperature that is available inside. As a result, it might crack. Through those cracks, the atmospheric air can move in. As a result, the whole lot what that was added in, it will burn into ashes. So in order to ensure that it doesn't happen, it has to be monitored 24/7. And this happens after 2 or 3 days. Now see here, initially the hole was made at the top. All those smokes available in the whole process are being exhausted. And see here, he is also carrying water. Again, I'm just informing you, like water in Ramnad, it is costly. Availability of water is very scarce over there. It is costly. This is the initial stage. After some 2 or 3 days of time, what they do is that they arrest these holes. These holes will be arrested. These holes will be plugged. Additional holes will be laid at the intermediate area. As a result, we make the flame to move down. And at the end of the day, the holes will be shifted down. And these layers would be covered with the wet soil. These layers would be covered, and the wetness of the soil would be ensured as a result by having the water sprayed over here. As a result, the whole soil structure would be remaining intact. We'll be able to prevent the air entry into it. As a result, combustion of the wood will not happen. Carbonization alone happens. And see, This was a batch what they have done as of now, approximately 8 to 10 days of time would have taken. And here you can see the adjacent batch what they have it over here. There is also another batch over here, and this is another batch which was done with the unburns what that was left over from the earlier batch. I'll be able to inform you about this one now. Okay, after this process is done, it will be allowed to cool, and after it is being done, it will be uncovered. The soil what that was layered, the paddy hay would have got burnt, the soil would have got mixed along with that one. It will be uncovered. Pollusive process as such, and people toil on it, they struggled on it, and they segregate of char and unburns. The unburns is segregated and it is being piled up. It is not a waste. They have the process repeated on this unburns again. They have the whole process repeated on this unburns again. They'll be able to convert this one also into a char. And after this, they'll be able to have the prices fixed, and they'll be able to pack in sacks and it will be sold. Charcoal. There are several observations. I don't want to highlight about all these things and all. These are general things. I'll be able to share the images. It becomes easier for you people to have it done. And with this one, we were approached by our government and they were asking us to design an eco-friendly charcoal kiln, which is more efficient as compared to the existing one. So the one basic thing what we have done was the baseline wasn't available. Rather, the people were not doing in an analytical way. They were not weighing the quantity of wood they employ, nor they have the weight of the charcoal what they get. Rather, their efficiency wasn't established as such. The yield wasn't aware by them. Then we have gone for all these analysis. Again, since I have a lower time, I'm having these things skipped. We have taken 11 batches. Out of those 11 batches, since blocks is being done, almost 50% of our sample size was this one batch. The remaining 25% were this one, fix and roots. And we were having these things done. We were able to weigh the amount of raw wood what we add onto it. And after the yield was done, we were also able to establish how much amount of charcoal they were able to get. These were the 4 places in which we have done the trials, with 11 sites and with 3 different types of things, logs, woods, and twigs. This was the initial weighed wood and unburns, all those things, and approximately these were the amount of yields what they were able to have it across. And this, if at all you see, the average trend happens like this one, and they were able to have the yield varying from 32% to 46%. This 46 was wrong, and approximately the average yield has to be between 32 to 35%. Okay. We were also came to know about existing of another alternative improvised technique, which we named it as Igloo Technique, which was done in Haridwar areas and all. So this is the practice what they do and here this is the structure what they make. Earlier in the conventional process, the wood was made into one heap, and onto the heap they were having those environments whereby the air entry was avoided. They were packing it with the paddy hay, they were having it with the soil, all those things and all, and then accordingly they were having it done. Whereas in the Haridwar method or the Igloo method, what they do is that they have these modes, igloo constructions. As a result, they have all these things and all. Only one opening would be there. They make all these things and all structures. This opening alone would be there. So this structure will be remaining intact for all the other batches and all. What they do is that once when they stack the whole igloo with wood, they'll be covering these things also with bricks. It will be covered with bricks as such, and then accordingly it will be plastered so that the air entry will be avoided. These are the openings what that is available for the air to come out, for the smokes to come out. And it will be closed and it will be uncovered as per the need. And they stacked the wood over here, and they were doing all these things and all. And then the one opposite practice is that in the earlier one, people were igniting it from the top, and here they were igniting it at the bottom. And then and after the whole process was over, the cover will be uncovered, or else the entry provision would be uncovered. Whatever which was available as wood earlier, it would have got converted into this charcoal. Yeah, on the analysis wise, what we have understood was the stacking time in the conventional, it takes 2 to 3 days approximately, whereas in Igloo it takes only 2 to 3 hours of time. And carbonization process, it takes approximately 6 days over here. Whereas in igloos, it takes 5 days over here. Yeah, the cooling time earlier it was 2 to 3 days, whereas here it is hardly a day. And uncovering and the other process it was taking 2 days of time, whereas here it is having only 2 hours of time. The igloo technique is far more improvised as compared to the existing one, but one problem still exists, that is the emissions, whatever they have. The emissions, whatever they have, like, and these are the factors what we had into account for the charcoal kiln, what we people have made. Like, it has to be easy to operate, it has to be rugged, manpower wise, it has to be operated by the layman also. Water demand has to be zero, electricity has to be zero, it should have a higher yield and it should have lower emissions. With these approaches, we have gone in for our lab and we have done all these setups and all. And we have gone in for allothermal method. See, the options what the earlier 2 methods were having it done. It was autothermal method. Autothermal means the wood, what has to be converted into charcoal will burn. It will give heat for the process. The heat for the process would be obtained by burning that wood itself. Okay, so it is called as autothermal method. And here we have gone in for allothermal method, whereby the heat will be supplied externally. So this was the arrangement what we people have made, and we were burning the fuel over here. Probably rather than this, I'll be able to show you in this image. It becomes easier. Any waste wood that was available, it can be burnt. The flue gas what that was available from the wood will be sent back into this rectangular chamber. This is the chamber whatever we have made onto this rectangular chamber where the wooden logs will be available. It will be made and the flue gas will be made to pass through this one. The flue gas also will be made at the bottom, like this will be able to heat it. This flue gas also will be able to heat it. The hot flue gas will be let out through this stack, like. And after the temperature has reached approximately 240, what we will do is that once when the volatile matter oozes out, what we do is that we will close this damper. This damper, what that was available over here, it will be closed. As a result, volatile matter, what that was available over here, which will come over through these holes, and it will be aiding this fuel. As a result, it will also get burnt. The flue gas will go at the underneath. As a result, we are able to avoid the emissions also. After the high temperature is over, this damper will be closed. Volatile matter that is available inside these wood will be driven off, and it will be made to come to this area where you have the existing flame. Like this one also will burn over here. So the high temperature air alone will be available over here. The whole process will happen. As a result, we were able to have this done, and it was a yield what we were able to get, like. And analysis wise, if at all we see, so the carbon content whatever we have got in our technique, it was approximately 88% as compared to the other two techniques, like allothermal method. The heat content also was higher, right? Apart from that, the quality is far better. Quality is far better, and some CFD analysis also was done so that we were able to have the exhaust gases removed. Like these are the advantages, like, and it was implemented at the field level also, and it was adopted by the people, like. Okay, thank you.
Thank you, sir. Thank you so much for your insightful talk on this carbonization. I hope participants are very much get benefit from this your talk, sir. Thank you so much, sir.
Thank you all, sir.
Thank you.